Imagine this. You're standing in your backyard on a clear night, looking up at that brilliant point of light hanging in the darkness. That's Jupiter, the gas giant that has captured human imagination for millennia. We're embarking on an incredible journey to understand not just how long it takes to reach Jupiter, but what that journey reveals about the true scale of our solar system and our place within it. If you're curious about this cosmic journey and want to explore more mysteries of our universe, subscribe to the channel and give this video a like. Your support is the biggest fuel to keep this channel going. Let's get started. Let's start with the most basic question. How far away is Jupiter? The answer changes constantly as both Earth and Jupiter orbit the Sun at different speeds. When the planets are at their closest approach, called opposition, Jupiter sits roughly 390 million miles from Earth. When they're on opposite sides of the Sun, that distance stretches to over 550 million miles. To put this in perspective, if Earth were a marble sitting on your kitchen table, Jupiter would be another marble sitting somewhere between 7 and 10 football fields away. But distance alone doesn't tell the full story of interplanetary travel. You can't simply point a spacecraft at Jupiter and fire the engines, because by the time you arrive, Jupiter will have moved to a completely different location in its orbit. Instead, spacecraft must follow carefully calculated trajectories that account for the gravitational influences of multiple planets, the changing positions of worlds, and the fundamental physics of orbital mechanics. The first successful mission to Jupiter was Pioneer 10, launched by NASA on March 2, 1972. This groundbreaking spacecraft took exactly 640 days to reach the giant planet, becoming the first human-made object to travel beyond the asteroid belt and encounter one of the outer planets. Pioneer 10's journey time of roughly 21 months established a benchmark for future missions and proved that interplanetary travel to the outer solar system was not just theoretically possible, but practically achievable. Pioneer 11 followed in 1973, taking a slightly different trajectory that allowed it to reach Jupiter in just under 2 years. These twin missions revolutionized our understanding of Jupiter, revealing it to be a complex world with a powerful magnetic field, intense radiation belts, and a retinue of fascinating moons that would captivate scientists for decades to come. The travel time to Jupiter depends critically on the type of mission you're planning. A flyby mission, where the spacecraft simply passes by the planet to take pictures and measurements before continuing into space, can take the most direct and fastest route. These missions typically take between 1.5 to 3 years, depending on the specific launch window and trajectory chosen. But if you want to study Jupiter in detail, you need an orbiter mission that can slow down enough to be captured by the planet's gravity and enter a stable orbit. This requires carrying extra fuel for orbital insertion maneuvers, which adds mass and complexity to the spacecraft. It also often means taking a longer, more indirect route that might include gravity assists from other planets to build up enough speed for the journey. The Galileo mission, launched in 1989, took an incredibly circuitous route to Jupiter that included flybys of Venus and Earth to gain the necessary velocity for its journey. This gravitational slingshot trajectory extended Galileo's travel time to 6 years, but it allowed the spacecraft to carry enough equipment to become the first mission to orbit Jupiter and study the planet and its moons in unprecedented detail. Gravity assists represent one of the most elegant solutions to the challenge of interplanetary travel. When a spacecraft flies past a planet, it can steal a tiny amount of the planet's orbital energy, using the planet's own motion around the Sun to accelerate toward its destination. It's like catching a ride on a cosmic moving walkway, allowing spacecraft to reach velocities that would be impossible with rocket engines alone. The Cassini mission to Saturn used this technique masterfully, flying past Venus twice, then Earth, then Jupiter, building up speed with each encounter. During its Jupiter flyby in December 2000, Cassini gained enough velocity to continue on to Saturn while simultaneously conducting valuable observations of the Jupiter system. This kind of multi-planet trajectory planning requires extraordinary precision, with spacecraft trajectories calculated years in advance to take advantage of the precise alignment of worlds. The New Horizons mission, which famously visited Pluto, used Jupiter as a gravitational springboard in February 2007. The spacecraft's encounter with Jupiter not only accelerated it toward the outer solar system, but also provided an opportunity to test instruments and conduct observations that improved our understanding of the giant planet's atmospheric dynamics and moon system. Juno, NASA's current mission orbiting Jupiter, took a more direct approach, launching in August 2011 and arriving at Jupiter in July 2016. This 5-year journey was specifically designed to minimize mission cost and complexity, while still allowing the spacecraft to carry sophisticated instruments for studying Jupiter's interior structure, magnetic field, and atmospheric composition. Each of these missions has revealed new aspects of Jupiter that challenge our understanding of how giant planets form and evolve. Jupiter isn't just a ball of gas sitting in space. It's a dynamic, complex world with a rich atmospheric structure, a powerful magnetic field that extends millions of miles into space, and a family of moons that include some of the most intriguing worlds in our solar system. Europa, one of Jupiter's 4 largest moons, harbors a subsurface ocean that contains more water than all of Earth's oceans combined. Io, the innermost large moon, is the most volcanically active world in the solar system, with sulfur plumes shooting hundreds of miles into space. Ganymede, the largest moon in the solar system, has its own magnetic field and may also harbor a subsurface ocean. These discoveries have transformed our understanding of where life might exist in our solar system and beyond. The challenge of reaching Jupiter extends far beyond simply calculating the right trajectory. Spacecraft venturing to the outer solar system face a hostile environment that pushes the boundaries of human engineering. Solar panels, which power most spacecraft near Earth and Mars, become increasingly ineffective as you move away from the Sun. At Jupiter's distance, sunlight is 25 times weaker than at Earth, making solar power generation extremely challenging. This is why many Jupiter missions have relied on radioisotope thermoelectric generators, or RTGs, which convert the heat from decaying plutonium into electricity. These nuclear power sources provide reliable energy for decades, but come with their own engineering challenges and safety considerations. The Voyager spacecraft, launched in 1977, still transmit data from interstellar space thanks to their RTGs, though their power output has steadily declined over the decades. Communication presents another fundamental challenge for Jupiter missions. Radio signals traveling at the speed of light take between 35 and 52 minutes to travel from Earth to Jupiter, depending on the planet's relative positions. This means that real-time control of spacecraft is impossible. By the time mission controllers on Earth see that something has gone wrong, the event happened nearly an hour ago. Spacecraft must be programmed with sophisticated autonomous systems capable of making critical decisions without human intervention. The radiation environment around Jupiter poses perhaps the greatest threat to spacecraft electronics and instruments. Jupiter's magnetic field traps charged particles, creating radiation belts far more intense than anything found around Earth. During each orbit, Juno passes through these radiation zones, subjecting its electronics to the equivalent of 100 million dental X-rays. Engineers had to develop specialized shielding, including a titanium vault that protects the spacecraft's most sensitive components from this punishing environment. But let's shift perspective for a moment and imagine you're not sending a robotic probe, but planning a crewed mission to Jupiter. This transforms the challenge from merely difficult to almost incomprehensibly complex. The longest continuous time humans have spent in space is just over a year aboard the International Space Station, and that's with regular resupply missions from Earth. A round trip to Jupiter would take a minimum of 3 to 4 years, and more likely 5 to 6 years for a mission that actually enters orbit around the giant planet. The psychological challenges of such a journey would be unprecedented. Astronauts would watch Earth shrink to a pale blue dot, indistinguishable from the stars. Communication delays would make real-time conversations with loved ones impossible. The crew would need to be entirely self-sufficient, capable of handling any medical emergency, equipment failure, or interpersonal conflict that might arise during years of isolation in the cosmic void. The physical effects of prolonged spaceflight present equally daunting challenges. Without Earth's gravity, astronauts' bones lose calcium, muscles atrophy, and cardiovascular systems weaken. Current exercise protocols on the ISS help mitigate these effects, but we don't fully understand the consequences of spending years in deep space, far from Earth's protective magnetic field, and exposed to galactic cosmic radiation. Food, water, and air would need to be recycled with near-perfect efficiency. A crew of 6 astronauts on a 5-year mission would need approximately 54,000 pounds of food if they consumed 3,000 calories per day. Even with advanced recycling systems and perhaps some form of space agriculture, the mass requirements for life support alone would be staggering. The spacecraft itself would need to be a marvel of engineering, combining the functions of a home, laboratory, hospital, and repair shop. It would require radiation shielding far beyond anything currently used in space, propulsion systems capable of operating reliably for years, and backup systems for every critical component. The development and testing of such a vessel would likely take decades and cost hundreds of billions of dollars. Yet despite these challenges, serious proposals for crewed missions to the Jupiter system have been developed. NASA's Human Outer Planets Exploration Program studied concepts for missions to Jupiter's moon Callisto, which orbits far enough from Jupiter to avoid the worst of the radiation belts. These studies envision nuclear-powered spacecraft using advanced propulsion technologies that could reduce travel times and enable the transport of the massive life support systems required for multi-year journeys. The scientific rewards of human exploration of the Jupiter system would be extraordinary. While robotic missions have revealed incredible details about Jupiter and its moons, human explorers could conduct investigations with a flexibility and intuition that no robot can match. Imagine astronaut scientists descending into the ice caves of Europa, searching for signs of life in the dark ocean beneath. Picture human explorers witnessing Io's volcanic eruptions firsthand, or establishing research stations on Ganymede to study its unique magnetic field. Future technologies could dramatically reduce travel times to Jupiter. Nuclear electric propulsion, using nuclear reactors to power high-efficiency ion drives, could potentially cut journey times in half. More exotic concepts like fusion ramjets or antimatter propulsion remain in the realm of theoretical physics, but could one day enable trips to Jupiter in months rather than years. The Variable Specific Impulse, Magnetoplasma Rocket, or VSIMAR, represents a near-term technology that could revolutionize interplanetary travel. This engine uses radio waves to heat plasma to extreme temperatures, creating thrust far more efficiently than chemical rockets. A spacecraft equipped with a nuclear-powered VSIMAR engine could potentially reach Jupiter in just 14 months, though this technology has yet to be tested beyond laboratory conditions. Solar sails present another intriguing possibility for reducing travel times to the outer solar system. These gossamer structures use the pressure of sunlight to accelerate spacecraft without requiring any fuel. While acceleration is slow, it's continuous, potentially enabling very high velocities over time. The Japanese Space Agency, JAXA, successfully demonstrated solar sail technology with their Icaros mission, though scaling this up for Jupiter missions presents significant engineering challenges. But perhaps the most exciting developments in Jupiter exploration come from missions currently being planned. The European Space Agency's Jupiter Icy Moons Explorer, or JUICE, launched in April 2023 and will arrive at Jupiter in 2031 after an 8-year journey involving multiple gravity assists. This sophisticated spacecraft will study Jupiter's magnetosphere and conduct detailed observations of Europa, Ganymede, and Callisto. NASA's Europa Clipper mission, scheduled to launch in October 2024, will take a more direct route to Jupiter, arriving in 2030 after a 5.5-year journey. This mission will conduct dozens of close flybys of Europa, using ice-penetrating radar to map the thickness of the Moon's ice shell and search for subsurface lakes that might harbor conditions suitable for life. These missions represent the cutting edge of planetary exploration, but they also highlight how far we've come since Pioneer 10's first flyby over 50 years ago. Each mission builds on the discoveries of its predecessors, using improved technologies and refined techniques to answer questions that previous missions raised. The Chinese National Space Administration has announced plans for their own Jupiter mission, tentatively scheduled for launch in the late 2020s. This would include an orbiter to study the planet and a possible probe to explore the atmosphere, marking China's entry into outer solar system exploration and demonstrating how Jupiter continues to captivate scientists and engineers worldwide. Private space companies are also beginning to eye the outer solar system. While SpaceX and Blue Origin currently focus on near-Earth activities and lunar missions, both companies have discussed long-term visions that include exploration of the outer planets. The reduction in launch costs promised by reusable rockets could make ambitious Jupiter missions more economically feasible in the coming decades. Understanding the journey to Jupiter requires grappling with the fundamental physics of orbital mechanics, a discipline that transforms the simple question, how long does it take, into a complex dance of mathematics, engineering, and cosmic timing. Unlike driving a car where you can simply point toward your destination and go, space travel operates in a realm where everything is constantly moving, and the shortest distance between 2 points is almost never a straight line. The concept of launch windows becomes crucial when planning any mission to Jupiter. These windows represent brief periods when Earth and Jupiter are positioned favorably for spacecraft to make the journey with minimum fuel expenditure. For direct trajectories to Jupiter, these optimal windows occur approximately every 13 months when Earth laps Jupiter in their respective orbits around the Sun. Missing a launch window doesn't just delay your mission by a few days or weeks, it can add years to your journey time or require so much additional fuel that the mission becomes impossible with current technology. The Galileo mission experienced this firsthand when the Challenger disaster in 1986 forced a delay that required completely redesigning the spacecraft's trajectory, adding years to its eventual journey time. The mathematics behind these trajectories involves solving what physicists call the three-body problem, accounting for the gravitational influences of the Sun, Earth, and Jupiter simultaneously. Unlike the elegant solutions possible for two gravitating bodies, the three-body problem has no general closed-form solution, requiring powerful computers to calculate precise trajectories through numerical integration. But here's where the story becomes even more fascinating. Spacecraft don't travel through empty space. They navigate through a complex gravitational landscape shaped by the Sun and all the planets. Lagrange points, positions where gravitational forces balance, create natural parking spots and gravitational highways that spacecraft can exploit. The Jupiter-Sun L1 point, located about 30 million miles sunward of Jupiter, provides a natural staging area for missions studying the planet's interaction with the solar wind. The concept of delta V, the change in velocity required for orbital maneuvers, governs everything about space travel. Reaching Jupiter from Earth requires a total delta V of approximately 9.6 kilometers per second, assuming an optimal Hohmann transfer orbit. To put this in perspective, escaping Earth's gravity well alone requires 11.2 kilometers per second, meaning the journey to Jupiter actually requires less additional velocity than the initial escape from our home planet. This counterintuitive fact reveals one of the beautiful efficiencies of orbital mechanics. Once you've broken free of Earth's gravity, you're already traveling at Earth's orbital velocity around the Sun, roughly 30 kilometers per second. Reaching Jupiter becomes a matter of adding or subtracting velocity at precisely the right moments to reshape your solar orbit into one that intersects with the giant planet. The Hohmann transfer, named after German engineer Walter Hohmann, who described it in 1925, represents the most fuel-efficient path between two circular orbits. For Earth to Jupiter, this trajectory takes approximately 2.7 years, tracing an elliptical arc that touches Earth's orbit at one end and Jupiter's at the other. It's the cosmic equivalent of coasting downhill, using the sun's gravity to carry you across the solar system with minimal fuel expenditure. But fuel efficiency comes at the cost of time. Faster trajectories require more aggressive departure velocities, consuming exponentially more fuel due to the tyranny of the rocket equation. This fundamental relationship between fuel and velocity means that cutting your travel time to Jupiter from 2.7 years to 2 years might double or triple your fuel requirements, while attempting to reach Jupiter in under a year could require impossible amounts of propellant. This is where gravity assists become game changers. By threading a spacecraft through carefully planned encounters with inner planets like Venus or Earth, mission planners can effectively steal orbital energy from these worlds to boost their spacecraft's velocity. The Cassini mission's trajectory, often called the Grand Tour, used 4 gravity assists to reach Saturn, gaining the equivalent of 75,000 miles per hour of delta V without burning a drop of fuel. The precision required for these gravity assists borders on the miraculous. Missing your aim point by just a few miles during a planetary flyby can result in trajectory errors that compound over millions of miles, potentially causing you to miss your target entirely. Navigation teams use the Deep Space Network's massive radio dishes to track spacecraft positions with extraordinary accuracy, measuring velocities to within millimeters per second across billions of miles of space. But even perfect navigation can't overcome the fundamental challenge that Jupiter presents to visiting spacecraft: its enormous gravity well. Jupiter's mass, 318 times that of Earth, creates an immense gravitational field that accelerates approaching spacecraft to tremendous velocities. The Galileo atmospheric probe entered Jupiter's atmosphere at 47.8 kilometers per second, making it one of the fastest human-made objects ever to impact a planetary body. This brings us to one of the most critical phases of any Jupiter mission: orbital insertion. A spacecraft approaching Jupiter on a typical interplanetary trajectory is traveling far too fast to enter orbit naturally. Without a significant braking maneuver, it would simply fly past the planet and continue into the outer solar system. The fuel required for this orbital insertion burn represents a major fraction of the spacecraft's total mass. Juno's orbital insertion on July 4, 2016, required a 35-minute engine burn that changed the spacecraft's velocity by 542 meters per second. During this critical maneuver, Juno was out of contact with Earth, operating entirely on pre-programmed instructions. Mission controllers could only wait anxiously for the spacecraft to re-establish contact and confirm that the burn had succeeded. The shape of a spacecraft's orbit around Jupiter dramatically affects its mission timeline and scientific capabilities. Juno follows a highly elliptical 53-day orbit that carries it close to Jupiter's cloud tops before swinging out beyond the orbit of Callisto. This orbit was specifically designed to minimize radiation exposure while maximizing scientific observations during close approaches. Alternative mission architectures could significantly change travel times to the Jupiter system. Aerocapture, a theoretical technique where spacecraft use atmospheric drag to slow down instead of rocket engines, could enable much faster transit times by allowing spacecraft to carry less fuel and more scientific instruments. However, the engineering challenges of surviving a high-speed passage through Jupiter's upper atmosphere have so far prevented this technique from being used. The future of Jupiter exploration might involve entirely new approaches to the journey. Nuclear pulse propulsion, famously studied in the 1960s under Project Orion, could theoretically propel massive spacecraft to Jupiter in less than a year by detonating nuclear explosives behind a pusher plate. While politically and environmentally problematic, the physics of such systems demonstrates that dramatically reduced travel times are theoretically possible with sufficient energy input. Ion drives, already used successfully on missions like Dawn and Hayabusa, offer another path to faster Jupiter missions. These engines accelerate xenon ions to extremely high velocities, providing gentle but continuous thrust over months or years. While individual ion engines produce thrust measured in fractions of a newton, their exceptional fuel efficiency enables mission profiles impossible with chemical rockets. The Bepicolombo mission to Mercury demonstrates advanced ion propulsion in action, using 4 xenon ion thrusters to navigate the complex trajectory required to reach the innermost planet. Similar technology scaled up for Jupiter missions could enable faster transits while carrying more scientific instruments and potentially even sample return capsules from Jupiter's moons. But perhaps the most intriguing possibility for future Jupiter missions involves harvesting resources from the Jupiter system itself. The moon Europa contains vast quantities of water that could be electrolyzed into hydrogen and oxygen rocket fuel. A mission that refuels in the Jupiter system could carry far more scientific equipment on the outbound journey, knowing that fuel for the return trip awaits at the destination. This in-situ resource utilization could transform Jupiter from a distant destination into a gateway to the outer solar system. Spacecraft could use Jupiter's moons as refueling stations, its enormous gravity as a slingshot to reach even more distant targets, and its magnetosphere as a natural particle accelerator for physics experiments impossible anywhere else in the solar system. Let's pause for a moment and consider what it means to spend years of your life traveling through the darkness between worlds. When the Apollo astronauts journeyed to the moon, they could still see Earth as a blue marble hanging in space, a constant reminder of home. But travelers to Jupiter would watch Earth fade until it becomes indistinguishable from the stars. A point of light no brighter than Venus appears from our backyard. This psychological dimension of the journey to Jupiter reveals profound truths about human nature and our relationship with the cosmos. The farthest any human has traveled from Earth is roughly 248,000 miles, achieved by the Apollo 13 crew during their emergency loop around the Moon. Jupiter, at its closest, lies over 1,500 times farther away. It's a distance that challenges not just our technology, but our very conception of what constitutes a journey. Ancient astronomers knew Jupiter as the wandering star, tracking its stately progression through the zodiac over the course of nearly 12 years. The Babylonians called it Marduk after their patron deity, while Chinese astronomers knew it as the wood star, associating it with the element of growth and expansion. These ancient observers could never have imagined that one day their descendants would send robotic emissaries to visit this distant light. Galileo's discovery of Jupiter's 4 largest moons in 1610 revolutionized our understanding of the cosmos. Here was proof that not everything orbited Earth, that other worlds could have their own satellites, their own systems. Those 4 dancing points of light, visible through even modest binoculars today, became the first indication that the universe was far more complex and wonderful than anyone had imagined. But knowing Jupiter exists and actually traveling there are vastly different propositions. If you could drive a car to Jupiter at highway speeds, the journey would take over 4,000 years. If you could fly in a commercial airliner, it would still take over 50 years of continuous flight. These comparisons help us grasp the enormous gulf between intellectual understanding and visceral experience of cosmic distances. The Voyager missions transformed our relationship with Jupiter from one of distant observation to intimate encounter. When Voyager 1 arrived at Jupiter in March 1979, it revealed a world of stunning complexity. The Great Red Spot, observed from Earth for over 3 centuries, was revealed to be a storm system larger than our entire planet, with wind speeds exceeding 400 miles per hour. But perhaps Voyager's most stunning discovery was Io's volcanic activity. Linda Morabito, a young navigation engineer, noticed an unusual bulge on the limb of Io while analyzing navigation images. This bulge turned out to be a massive volcanic plume, marking the first observation of active volcanism beyond Earth. In that moment, Jupiter's moon transformed from a point of light into a dynamic world with its own geological story. The journey to Jupiter challenges us to think about time in new ways. Mission planners must account for where Jupiter will be years in the future. calculating trajectories based on orbital mechanics that have been refined over centuries. They're essentially throwing a dart at a moving target from a moving platform, with both thrower and target following complex paths through three-dimensional space. This temporal dimension of space travel connects us to deep questions about human purpose and patience. We live in an era of instant gratification, where information travels around the globe in milliseconds, and next-day delivery is considered slow. Yet reaching Jupiter requires a commitment to goals that won't be achieved for years or even decades. The scientists who plan these missions often retire before their spacecraft reach their destinations. Consider the team that designed and built the Galileo spacecraft in the 1980s. They worked for years on a mission that wouldn't reach Jupiter until 1995. Many of those engineers and scientists had moved on to other projects or retired by the time Galileo entered orbit, yet they dedicated their careers to a journey they might not see completed, driven by the pure desire to expand human knowledge. This long-term thinking extends to the spacecraft themselves, which must be built to survive not just the journey, but years of operation in Jupiter's harsh environment. Every component must be tested to function after years of exposure to cosmic radiation, temperature extremes, and the mechanical stresses of launch and orbital insertion. Engineers must anticipate failures that might occur years in the future and design redundancies and workarounds. The communication delay between Earth and Jupiter adds another layer of complexity to these missions. When Juno performs its close flybys of Jupiter, skimming just 3,000 miles above the cloud tops, mission controllers on Earth are essentially watching history. By the time they receive the data, the spacecraft has already completed its pass and is heading back out into space. This time, delay transforms mission operations from active control to careful preparation and patient observation. But these challenges pale in comparison to what future human explorers will face. Imagine spending years in a spacecraft no larger than a house with the same handful of people, knowing that Earth is too far away to offer any help if something goes wrong. The psychological profiles of such explorers would need to be extraordinary, combining technical expertise with emotional resilience and the ability to find meaning in isolation. Science fiction has long grappled with these challenges, envisioning generation ships where multiple human lifetimes pass during the journey, or suspended animation technology that allows crews to sleep through the years of transit. While these remain fictional solutions, they highlight the fundamental challenge that Jupiter's distance presents to human ambitions. Yet the scientific rewards of reaching Jupiter justify these extraordinary efforts. Jupiter is often called a failed star, containing many of the same elements as the Sun, but lacking the mass necessary to ignite nuclear fusion. Studying Jupiter helps us understand not just our own solar system's formation, but the processes that create planetary systems throughout the universe. The metallic hydrogen believed to exist in Jupiter's core represents a state of matter that cannot be reproduced in Earth laboratories. The planet's powerful magnetosphere accelerates particles to near light speed, creating a natural laboratory for high-energy physics. The complex interactions between Jupiter and its moons reveal tidal forces and orbital resonances that help us understand similar processes throughout the cosmos. Each mission to Jupiter has revealed new mysteries that demand further exploration. Juno's discovery of Jupiter's lumpy gravitational field suggests the planet's interior is far more complex than previously thought. The detection of water deep in Jupiter's atmosphere provides clues about how the planet formed and migrated to its current position. These findings reshape our understanding of planetary formation throughout the universe. The journey to Jupiter also serves as a stepping stone to even more distant destinations. Many missions to Saturn, Uranus, and Neptune have used Jupiter gravity assists to reach their targets. The New Horizons mission to Pluto gained 4,000 miles per hour of velocity from its Jupiter flyby, cutting years off its journey to the edge of the solar system. In this way, Jupiter serves as a cosmic accelerator, helping us reach even more distant worlds. The technological innovations driven by the challenge of reaching Jupiter benefit society in unexpected ways. The miniaturization required for spacecraft computers has contributed to the development of consumer electronics. The image processing techniques developed to handle data from Jupiter missions have found applications in medical imaging. The project management methodologies required for multi-year missions have influenced how we approach complex engineering projects on Earth. The story of reaching Jupiter is ultimately a story about human curiosity, pushing against the boundaries of what's possible. Every mission represents thousands of people working together across decades, united by the shared goal of understanding our cosmic neighborhood. This collaboration transcends national boundaries, political differences, and cultural divides, reminding us that the quest for knowledge is one of humanity's most noble endeavors. When we talk about the journey to Jupiter, we're really discussing multiple journeys happening simultaneously. There's the physical journey of the spacecraft, crossing hundreds of millions of miles of space. There's the technological journey, pushing the boundaries of engineering and computer science. There's the scientific journey, transforming raw data into understanding. And there's the human journey, as our species gradually extends its reach into the cosmic ocean. The economics of Jupiter exploration reveal fascinating truths about human priorities. A typical mission to Jupiter costs between $1 and $3 billion, spread over 15 to 20 years from initial concept to end of operations. This might seem expensive until you consider that humanity spends more on cosmetics in a single year than we've spent on all Jupiter missions combined. The choice to explore Jupiter represents a deliberate decision to invest in knowledge and wonder rather than immediate gratification. Each mission builds upon the legacy of those that came before. When Juno arrived at Jupiter, it carried instruments specifically designed to investigate mysteries uncovered by Galileo 2 decades earlier. Future missions like Europa Clipper will follow up on tantalizing hints of habitability discovered by previous spacecraft. This continuity of exploration spans human generations, with each mission answering old questions while raising new ones. The international nature of Jupiter exploration demonstrates humanity at its best. The European Space Agency's JUICE mission includes contributions from Japan, Israel, and the United States. NASA missions regularly carry instruments built by international partners. Data from all missions is shared freely with scientists worldwide. In the journey to Jupiter, we see a model for how humanity can work together on challenges that benefit all of us. But let's return to the fundamental question of time and distance. The minimum energy trajectory to Jupiter, following a Hohmann transfer orbit, takes about 2 years and 8 months. But this assumes you launch at exactly the right time and follow the most fuel-efficient path. Miss your launch window by even a few days, and you might add months to your journey time or need substantially more fuel to reach your destination. The fastest spacecraft ever to visit Jupiter was New Horizons, which made the journey in just 405 days. But this record comes with an important caveat. New Horizons was on a flyby trajectory, using Jupiter's gravity to slingshot toward Pluto. It zoomed past Jupiter at over 50,000 miles per hour, too fast to enter orbit. This highlights a fundamental trade-off in space travel: speed versus the ability to stop and study your destination. Future technologies might dramatically reduce travel times to Jupiter. Fusion rockets, if successfully developed, could provide specific impulses 10 times greater than chemical rockets, potentially cutting journey times to months rather than years. Breakthrough Propulsion Physics, a NASA program that investigated exotic concepts like warp drives and wormholes, explored whether the laws of physics might permit even faster travel, though no practical technologies emerged from this research. Solar electric propulsion represents a nearer-term technology that could revolutionize Jupiter missions. By using solar panels to power ion engines near Earth, then switching to nuclear power in the outer solar system, spacecraft could maintain continuous thrust throughout their journey. This constant acceleration could reduce travel times while actually using less propellant than conventional rockets. The concept of cycler orbits offers another intriguing possibility for regular transportation to Jupiter. Just as Buzz Aldrin proposed Mars cyclers that would continuously orbit between Earth and Mars, Similar trajectories could be established between Earth and Jupiter. Large habitats could follow these orbits permanently, with smaller spacecraft ferrying crew and supplies during each encounter. This would transform the journey to Jupiter from a one-time expedition into a regular transportation route. But perhaps the most important aspect of the journey to Jupiter is what it teaches us about our place in the universe. Every mile we travel away from Earth is a mile into the unknown, a step into a cosmos that dwarfs our everyday experience. The vastness of space between Earth and Jupiter, empty except for the occasional asteroid or comet, reminds us how precious and unusual planets are in the cosmic void. The radiation environment encountered during the journey to Jupiter provides sobering reminders of how finely tuned Earth is for life. Beyond Earth's protective magnetosphere, cosmic rays and solar particles bombard spacecraft with radiation levels that would be lethal to unprotected humans. The journey to Jupiter takes us through this hostile environment for years, requiring sophisticated shielding and careful mission planning to protect both equipment and potential future crews. Navigation during the long journey requires extraordinary precision. Spacecraft must track their position relative to stars, using celestial navigation techniques refined over centuries of seafaring, but adapted for three-dimensional space. The Deep Space Network's giant radio dishes serve as cosmic lighthouses, providing reference points for spacecraft to determine their position and velocity with incredible accuracy. The silence of space during the journey to Jupiter is profound. No air means no sound, no weather, no change, except the slow dance of distant stars wheeling through the spacecraft's windows. For robotic missions, this silence is merely a technical challenge. For future human missions, it will be a psychological reality that no amount of training can fully prepare for. Yet this isolation also offers unique opportunities for scientific observation. Far from the electromagnetic noise of Earth, spacecraft traveling to Jupiter can make measurements of the cosmic microwave background, search for gravitational waves, and study the solar wind with unprecedented clarity. The journey itself becomes a scientific mission, with discoveries possible throughout the transit. The patience required for Jupiter missions extends to the scientists who analyze the data. A single close flyby of Jupiter by Juno generates so much information that researchers will spend years extracting scientific insights. Graduate students who begin their careers analyzing data from current missions may spend their entire professional lives working with information gathered during a few crucial hours of close approach to Jupiter. This multi-generational aspect of Jupiter exploration connects us to the great cathedral builders of medieval Europe, who began projects they knew they would never see completed. Like those ancient architects and stonemasons, today's mission planners and engineers work on projects whose full impact won't be realized for decades. This long-term thinking represents humanity at its most forward-looking and optimistic. The cultural impact of Jupiter missions extends far beyond the scientific community. Images of Jupiter's swirling clouds have inspired artists, musicians, and writers. The discovery of ocean worlds like Europa has influenced science fiction and sparked public discussions about the possibility of extraterrestrial life. Each mission to Jupiter contributes to a gradual shift in human consciousness, as we begin to see ourselves as citizens of the solar system rather than just inhabitants of Earth. Educational programs built around Jupiter missions inspire new generations of scientists and engineers. Students track spacecraft positions, analyze real mission data, and participate in citizen science projects that contribute to actual research. The journey to Jupiter becomes a teaching tool that brings abstract concepts of physics and mathematics to life through real-world applications. As we dive deeper into understanding the journey to Jupiter, we encounter one of the most fascinating aspects of space exploration: how the destination itself affects the voyage. Jupiter isn't just a passive target waiting at the end of a long journey. It's an active participant in the cosmic dance, its massive gravity warping space around it, its magnetic field creating an invisible obstacle course that spacecraft must navigate, its system of moons offering both opportunities and challenges for exploration. The discovery of Jupiter's radiation belts by Pioneer 10 fundamentally changed how we approach missions to the giant planet. These belts, far more intense than Earth's Van Allen belts, can fry electronics and degrade solar panels in minutes. Mission planners must carefully design trajectories that minimize time spent in these hazardous zones while still allowing for meaningful scientific observations. It's like plotting a course through a minefield where the mines are invisible and constantly shifting. This radiation challenge has driven remarkable innovations in spacecraft design. Juno's titanium vault, weighing nearly 400 pounds, protects its sensitive electronics from radiation that would otherwise destroy them in a matter of hours. The spacecraft's orbit was carefully crafted to thread between the worst of the radiation belts, dipping close to Jupiter's cloud tops, where the magnetic field actually provides some protection before retreating to safer distances. But Jupiter's moons offer their own unique challenges and opportunities for exploration. Europa, perhaps the most tantalizing destination in the Jupiter system, orbits deep within the radiation belts. A spacecraft attempting to orbit Europa would accumulate lethal radiation doses in a matter of days. This is why the Europa Clipper mission will use a series of flybys rather than entering orbit, dipping in for quick observations before retreating to safer distances to transmit data back to Earth. The gravitational choreography required to explore Jupiter's moons pushes orbital mechanics to its limits. The Galileo mission pioneered the use of gravity assists within the Jupiter system itself, using close flybys of the moons to reshape its orbit without using precious fuel. Over its 8-year mission, Galileo performed 35 flybys of Jupiter's moons, each one precisely calculated to set up the next encounter while maximizing scientific observations. This technique, called a moon tour, transforms the challenge of exploring multiple worlds into an elegant solution. By carefully timing encounters with Io, Europa, Ganymede, and Callisto, spacecraft can essentially surf through the Jupiter system, using the moon's gravity to reach destinations that would otherwise require impossible amounts of fuel. It's celestial billiards on a cosmic scale, where understanding the physics allows you to visit dozens of worlds with a single spacecraft. The communication infrastructure required to support Jupiter missions represents another marvel of human engineering. The Deep Space Network's 70-meter antennas can detect signals from Jupiter that arrive with less power than a single snowflake falling to Earth. These whispers from across the solar system must be amplified and processed to extract the scientific data encoded within. A typical image from Juno takes nearly 50 minutes to travel from Jupiter to Earth, arriving as a stream of ones and zeros that must be reconstructed into the stunning images we see. But the data rates from Jupiter are painfully slow by modern standards. While you might download a movie in minutes on Earth, receiving the same amount of data from Jupiter can take days or weeks. Mission planners must carefully prioritize which observations to transmit, knowing that bandwidth limitations mean tough choices about what data makes the journey back to Earth. Every bit of information represents a decision about what's most important to understand about this alien world. The longevity required for Jupiter missions places extraordinary demands on spacecraft systems. Unlike missions to Mars that might last a few years, Jupiter explorers must function for decades. Voyager 1 and 2, launched in 1977, are still transmitting data from interstellar space over 45 years later. This reliability comes from redundant systems, careful component selection, and engineering conservatism that prioritizes durability over cutting-edge performance. Software updates become particularly challenging when your spacecraft is hundreds of millions of miles away. Programmers must anticipate problems that might arise years in the future and build in flexibility to handle situations they can't imagine. The Galileo mission famously overcame the failure of its main antenna by reprogramming the spacecraft to compress data in ways that weren't envisioned when it launched. This kind of remote problem-solving requires deep understanding of both the hardware and software systems. The human stories behind Jupiter missions reveal the dedication required to explore the outer solar system. Scientists spend entire careers focused on single instruments or investigations. Graduate students who join mission teams might become grandparents before their spacecraft reaches its destination. This long-term commitment requires a special kind of patience and faith in the scientific process that's increasingly rare in our fast-paced world. Consider the team maintaining the Voyager spacecraft. These engineers, many of whom have worked on the mission for decades, keep 45-year-old spacecraft functioning using documentation written on obsolete computers and expertise that exists nowhere else on Earth. They're like monks maintaining ancient knowledge, ensuring that humanity's most distant ambassadors continue their journey into interstellar space. The philosophical implications of the journey to Jupiter extend far beyond practical considerations of fuel and trajectories. Each mission represents humanity's attempt to transcend our biological limitations, to extend our senses across vast distances and comprehend scales that dwarf our everyday experience. When we receive images from Jupiter, we're seeing through robotic eyes what no human eyes have witnessed directly. It's a form of technological telepresence that would have seemed like magic to previous generations. This expansion of human perception changes how we understand our place in the cosmos. Jupiter, once just a wandering star to ancient astronomers, has become a complex world with weather patterns we can track, moons we've mapped in detail, and an interior we're beginning to understand through gravitational measurements. Each mission adds layers to our understanding, transforming abstract knowledge into visceral comprehension. The search for life in the Jupiter system adds urgency to these explorations. The discovery of hydrothermal vents on Earth's ocean floor, teeming with life in the absence of sunlight, revolutionized our understanding of where life might exist. Europa's subsurface ocean, kept liquid by tidal heating, might harbor similar conditions. The possibility that life could exist just a few 100 million miles away transforms the journey to Jupiter from pure exploration into a quest to answer one of humanity's most profound questions. Are we alone? Future missions to search for life in Europa's ocean face extraordinary technical challenges. Penetrating through miles of ice, surviving in a high-radiation environment, and operating autonomously in an alien ocean requires technologies that push beyond current capabilities. Yet the potential payoff, the discovery of life beyond Earth, justifies almost any effort. The journey to Jupiter becomes not just about reaching a destination, but about what we might find when we get there. The timeline for these life detection missions stretches decades into the future. The Europa Clipper will arrive in 2030, spending years conducting reconnaissance to identify the best locations for future landers. A follow-up mission to actually sample Europa's ocean might not launch until the 2040s, with results not available until the 2050s or beyond. This multi-generational approach to exploration requires institutional continuity and societal commitment that spans human lifetimes. Climate change on Earth provides an interesting parallel to the patience required for Jupiter exploration. Both challenges require long-term thinking, international cooperation, and the ability to work toward goals whose benefits might not be realized for decades. The same species that struggles to address climate change on generational timescales somehow finds the vision to plan missions to Jupiter that span similar periods. Perhaps space exploration serves as proof that humanity is capable of long-term thinking when properly motivated. The technological spillovers from Jupiter missions continue to benefit society in unexpected ways. The image processing algorithms developed to extract maximum information from limited bandwidth have applications in medical imaging and remote sensing. The fault-tolerant computing systems designed to survive years in space influence how we design critical systems on Earth. The materials science required to survive Jupiter's radiation environment contributes to advances in electronics and shielding technology. The question of how long it takes to reach Jupiter ultimately leads us to an even more profound question. What does it mean for humanity to become a spacefaring civilization? Every journey beyond Earth teaches us something about our capabilities, our limitations, and our destiny as a species. The path to Jupiter represents more than just a technical challenge. It's a stepping stone toward understanding our role in the cosmic story that's been unfolding for billions of years. When we examine the progression of space exploration, we see a pattern of expanding horizons that mirrors human development itself. Our ancestors first explored their immediate surroundings, then ventured across continents and oceans. The 20th century saw us take tentative steps beyond our atmospheric cradle, and the 21st century has begun to see regular human presence in low Earth orbit. The journey to Jupiter represents the next logical step in this progression, pushing our capabilities into the deep solar system. The concept of becoming a Type 1 civilization, as described by physicist Nikolai Kardashev, involves harnessing all the energy available on our home planet. But the journey to Jupiter points toward Type 2 status, where we would harness the energy of our entire solar system. Jupiter's moons represent vast reservoirs of water, minerals, and energy that could support human expansion throughout the outer solar system. The journey time to Jupiter becomes less important when viewed as a one-way trip to establish permanent outposts rather than a round-trip exploration mission. Consider the paradigm shift that permanent settlement of the Jupiter system would represent. Europa's subsurface ocean contains more water than all of Earth's oceans combined. Ganymede's magnetic field could provide protection from cosmic radiation. Callisto's distance from Jupiter places it outside the worst radiation belts while still providing access to the giant planet's resources. A civilization established in the Jupiter system would have access to resources that dwarf anything available on Earth. The engineering challenges of permanent settlement push us to develop technologies that seem like science fiction today. Closed-loop life support systems must achieve near-perfect efficiency to support populations for generations without resupply from Earth. Nuclear reactors must operate reliably for decades in the harsh radiation environment. Spacecraft must transform from temporary visitors into permanent homes capable of supporting human communities. But the psychological and social challenges might prove even more daunting than the technical ones. How do you maintain cultural continuity across generations born in space? How do you govern communities separated from Earth by years of travel time? How do you preserve human values and ethics in an environment where survival depends entirely on technology and cooperation? The journey to Jupiter becomes a journey toward understanding what it means to be human beyond Earth. The discovery of life in Europa's ocean, if it exists, would fundamentally change the calculation of how long it takes to reach Jupiter. A journey that seems impossibly long for exploration becomes urgent and necessary when viewed as first contact with alien life. The time scales involved in space exploration suddenly compress when faced with the possibility of answering one of humanity's most profound questions about our place in the universe. The astrobiology implications of Jupiter exploration extend far beyond the possibility of finding microbes in Europa's ocean. Jupiter's moons represent different experiments in planetary evolution, each one teaching us about the conditions necessary for life to emerge and thrive. Io's volcanic activity demonstrates how tidal forces can power geological processes. Europa shows us how ice can insulate subsurface oceans. Ganymede reveals how magnetic fields interact with radiation environments. Each moon is a laboratory for understanding habitability throughout the cosmos. The search for life also transforms our understanding of time in ways that connect to the journey duration. If life exists in Europa's ocean, it might have been evolving independently for billions of years, developing along pathways completely different from terrestrial evolution. The years required to reach Jupiter become insignificant compared to the eons of separate evolutionary history we might discover. We're not just traveling across space, but potentially across biological time, encountering the results of evolution that diverged from Earth's before complex life even existed on our planet. Future generations might view our current limitations in reaching Jupiter the way we view ancient limitations in crossing oceans. The Polynesians who first settled the Pacific Islands took enormous risks crossing thousands of miles of open ocean in canoes. Yet their descendants today fly the same distances in hours. Perhaps our descendants will routinely commute between Earth and Jupiter in timeframes that make current journey times seem quaint. The development of fusion propulsion could revolutionize travel to Jupiter, potentially reducing journey times from years to months. Project Prometheus, NASA's nuclear propulsion initiative, studied reactor designs capable of powering ion drives for decades of continuous operation. While political concerns ended the program, the physics remains sound. A fusion-powered spacecraft could maintain acceleration throughout its journey to Jupiter, providing both fast transit times and artificial gravity for human crews. Even more exotic propulsion concepts might eventually make Jupiter accessible on human timescales. Breakthrough Starshot's work on light sails demonstrates how photons can provide propulsion without requiring fuel. While current concepts focus on tiny probes to nearby stars, scaled-up versions might enable rapid transit to the outer solar system. The challenge lies in developing sails large enough and lightweight enough to accelerate meaningful payloads to useful velocities. The economic development of the Jupiter system could transform the entire solar system's economy. Jupiter's moons contain vast quantities of water ice that could be converted into hydrogen and oxygen rocket fuel. The giant planet's magnetosphere could serve as a natural particle accelerator for physics experiments impossible anywhere else. The low gravity of the moons makes them ideal locations for launching missions to even more distant destinations. This economic perspective changes how we calculate the value of the journey time to Jupiter. If Jupiter becomes a hub for outer solar system exploration, the initial investment in reaching it pays dividends for centuries. The moons could serve as refueling stations, research bases, and staging areas for missions to Saturn, Uranus, Neptune, and beyond. The journey to Jupiter becomes not an end in itself, but a crucial step toward exploring the entire outer solar system. The international cooperation required for permanent Jupiter settlements mirrors the cooperation needed to address global challenges on Earth. Climate change, pandemic response, and resource management all require the same kind of long-term thinking and collaborative effort needed for space exploration. Perhaps the journey to Jupiter serves as a test case for humanity's ability to work together on challenges that transcend national boundaries and individual lifetimes. The cultural impact of establishing permanent human presence in the Jupiter system would rival the impact of European exploration of the Americas. New forms of government, economics, and social organization would need to evolve to handle the unique challenges of life in space. Art, literature, and philosophy would need to grapple with experiences no human has ever had. The journey to Jupiter becomes a journey toward becoming a fundamentally different kind of civilization. Children born in the Jupiter system would be the first humans for whom Earth is not home but history. They would grow up seeing the Great Red Spot as a familiar weather pattern, knowing the phases of multiple moons, and thinking of interplanetary travel as routine. Their perspective on the universe would be fundamentally different from Earth-born humans, shaped by the unique environment of the outer solar system. The preservation of Earth's biosphere takes on new urgency when viewed from the perspective of Jupiter colonization. While establishing backup locations for human civilization provides security against existential threats, it also emphasizes how unique and precious Earth's environment truly is. The journey to Jupiter might ultimately teach us more about protecting our home planet than about conquering new worlds. As we contemplate the years required to reach Jupiter, we're really grappling with one of the most fundamental aspects of human nature: our relationship with time itself. In an age where we measure internet speeds in milliseconds and expect instant responses to our messages, the idea of dedicating years to a single journey challenges everything about how we normally think about goals and achievements. Yet this challenge might be exactly what we need to mature as a species. The concept of deep time in geology prepared us for understanding cosmic scales, but space exploration takes this even further. When geologists speak of millions or billions of years, they're discussing processes that happened in the past. When we plan missions to Jupiter, we're committing to processes that will unfold in our future. requiring faith that the institutions, technologies, and people involved will persist long enough to see them through. This temporal commitment connects space exploration to some of humanity's greatest achievements. The Gothic cathedrals of Europe took centuries to complete, with generations of craftsmen contributing to projects they knew they wouldn't live to see finished. The Great Wall of China was built over more than 2 millennia. The Manhattan Project compressed enormous complexity into just 3 years through unprecedented coordination and resources. Jupiter missions require all of these qualities: multi-generational vision, sustained effort, and intense coordination across diverse fields of expertise. The patience required for Jupiter exploration runs counter to many modern trends, but aligns with deeper human capabilities that we sometimes forget we possess. Indigenous cultures maintained oral traditions across thousands of years. Buddhist monasteries have preserved teachings and practices across centuries. Scientific institutions like the Royal Society have maintained continuous operation for over 360 years. The journey to Jupiter draws on these same human capacities for long-term thinking and institutional continuity. Consider how the timeline of Jupiter exploration maps onto human life stages. A mission that begins conception when you're in college might reach its destination when you're approaching retirement. The graduate students who work on early mission phases become the senior scientists who interpret the final data decades later. Mission scientists sometimes pass their responsibilities to their own children or students, creating intellectual lineages that span the entire duration of exploration programs. This intergenerational aspect of Jupiter exploration creates unique forms of scientific and personal legacy. Unlike most human endeavors, space missions create permanent records of their participants' work that will survive for centuries. The computers aboard Voyager 1 and 2 contain messages intended for any alien civilizations that might encounter them millions of years from now. Every Jupiter mission becomes a time capsule, preserving not just scientific data, but records of human achievement at specific moments in our technological development. The delayed gratification required for Jupiter missions contrasts sharply with the immediate feedback loops that dominate modern life. Social media provides instant responses to our thoughts. Video games offer immediate rewards for player actions. The stock market fluctuates minute by minute. Yet space exploration operates on entirely different timescales, requiring participants to find satisfaction in processes rather than outcomes, in progress rather than completion. This temporal mismatch might explain why space exploration sometimes struggles for public support despite its obvious importance. The benefits of Jupiter exploration won't be fully realized for decades, while the costs are immediate and tangible. Democratic societies, which operate on election cycles measured in years, must somehow commit to projects whose benefits span generations. This requires a form of political maturity that space exploration both demands and potentially helps develop. The educational timeline for Jupiter exploration reveals another fascinating aspect of deep time thinking. Students who study planetary science today using data from the Galileo mission are learning from information gathered when they were children or before they were born. The textbooks they read describe discoveries made years ago by instruments that no longer exist, orbiting a planet they may never visit in person. Yet this secondhand knowledge forms the foundation for planning missions that might not launch until those same students are established in their careers. Artificial intelligence and machine learning are beginning to compress some aspects of the Jupiter exploration timeline. Computer simulations can now model millions of years of planetary evolution in hours or days. AI systems can process years of spacecraft data in minutes, identifying patterns and anomalies that human scientists might miss. While these technologies can't eliminate the fundamental constraint of travel time, they're revolutionizing how we prepare for missions and analyze the data they return. The development of autonomous systems for Jupiter exploration reflects broader trends in robotics and AI that are transforming society on Earth. Spacecraft operating in the Jupiter system must make split-second decisions without human input, adapting to unexpected situations using pre-programmed instructions and machine learning algorithms. These same technologies find applications in autonomous vehicles, medical diagnostics, and environmental monitoring systems that benefit life on Earth. The materials science advances required for Jupiter missions demonstrate how space exploration drives innovation across multiple fields. The radiation-resistant electronics developed for spacecraft operating in Jupiter's harsh environment contribute to improved medical devices and nuclear power systems. The lightweight, durable materials needed for long-duration space missions find applications in automotive, aerospace, and consumer products. The journey to Jupiter becomes a catalyst for technological advancement that benefits society in ways completely unrelated to space exploration. Precision manufacturing required for Jupiter missions pushes the boundaries of human craftsmanship to extraordinary levels. Components must function flawlessly after years of storage, launch stresses, cosmic radiation exposure, and temperature cycling that would destroy most terrestrial equipment. The quality control and testing protocols developed for space applications influence manufacturing standards across industries, contributing to improved reliability and performance of everything from smartphones to medical implants. The international cooperation required for Jupiter exploration creates diplomatic and cultural connections that transcend the missions themselves. Scientists from different countries work together for decades on shared goals, building relationships that survive political tensions and economic fluctuations. The European Space Agency's JUICE mission includes contributions from multiple continents, creating networks of collaboration that influence scientific cooperation far beyond planetary science. Language barriers that might seem insurmountable on Earth become manageable when scientists share the common goal of understanding Jupiter. Technical diagrams, mathematical equations, and scientific principles provide universal vocabularies that enable communication across cultural and linguistic differences. The journey to Jupiter becomes a bridge between human communities that might otherwise remain isolated from each other. The philosophical implications of spending years traveling to Jupiter challenge fundamental assumptions about human purpose and meaning. If life's meaning comes from relationships, how do we maintain connections across the vast distances of space? If purpose comes from immediate impact, how do we find satisfaction in projects whose benefits won't be realized for decades? If happiness depends on familiar environments, how do we adapt to the alien landscape of the outer solar system? These questions become particularly relevant as we consider eventual human missions to Jupiter. Astronauts on multi-year journeys would need to develop new forms of meaning and purpose that don't depend on immediate feedback from Earth-based communities. They would become pioneers not just of space, but of consciousness itself, exploring what it means to be human when separated from the planetary environment that shaped our species' evolution. The psychological research conducted to support long-duration space missions provides insights into human resilience and adaptability that benefit mental health treatment on Earth. Isolation studies, stress management techniques, and group dynamics research developed for space exploration contribute to our understanding of how humans cope with extreme environments and social stress. The journey to Jupiter becomes a laboratory for studying human psychology under conditions impossible to replicate on Earth. The story of reaching Jupiter ultimately becomes a mirror, reflecting our deepest questions about human nature, purpose, and destiny. Every calculation of orbital mechanics, every design decision for radiation shielding, every choice about scientific instruments carries within it assumptions about what we value as a species and what kind of future we want to create. The years required to reach Jupiter aren't just about distance. They're about transformation, both of our technology and of ourselves. When we examine the history of human exploration, we see a consistent pattern. The journey changes the explorer as much as the destination. Magellan's crew returned from circumnavigating Earth with fundamentally different understanding of geography and navigation. The Apollo astronauts came back from the Moon with perspectives on Earth that influenced environmental movements for generations. Future travelers to Jupiter will return, if they return at all, with insights about humanity and the cosmos that we can barely imagine today. The radiation environment around Jupiter provides a perfect metaphor for how exploration transforms understanding. Before Pioneer 10's flyby, in 1973, scientists knew Jupiter had a magnetic field but grossly underestimated its intensity. The spacecraft's instruments were nearly overwhelmed by radiation levels 10,000 times stronger than predicted. This discovery forced a complete redesign of future missions and revolutionized our understanding of planetary magnetospheres throughout the universe. This pattern of unexpected discovery repeats throughout the history of Jupiter exploration. Every mission answers the questions it was designed to address while revealing entirely new mysteries that previous scientists couldn't have imagined. Galileo's detection of a subsurface ocean beneath Europa's ice created the field of astrobiology focused on ice-covered worlds. Juno's discovery that Jupiter's interior is far more complex than expected is forcing planetary scientists to reconsider how giant planets form and evolve. The recursive nature of scientific discovery means that the journey to Jupiter becomes less about reaching a destination and more about participating in an ongoing conversation between human curiosity and cosmic reality. Each mission represents humanity asking questions of the universe, and each set of results prompts new questions that drive the next generation of exploration. The timeline extends indefinitely because our capacity for wonder and inquiry appears to be infinite. This perpetual questioning connects Jupiter exploration to the deepest traditions of human intellectual development. The pre-Socratic philosophers of ancient Greece wondered about the nature of matter and motion, laying groundwork for physics that still guides spacecraft design today. Medieval Islamic astronomers developed mathematical techniques for predicting planetary positions that evolved into the orbital mechanics we use for Jupiter missions. The scientific revolution of the 16th and 17th centuries established experimental methods that every mission continues to refine and apply. The collaborative nature of modern Jupiter exploration represents an evolution in how humanity organizes knowledge-seeking activities. Unlike the solitary philosophers of antiquity or the small teams of early modern science, contemporary missions involve thousands of people working across multiple decades and continents. The European Space Agency's JUICE mission includes contributions from universities, laboratories, and companies across Europe, with collaboration from partners in Japan, Israel, and the United States. This global cooperation demonstrates humanity's growing capacity to organize complex projects that transcend traditional boundaries. The data management challenges of Jupiter missions reveal fascinating connections between space exploration and information science. A single close flyby of Europa by the Europa Clipper mission will generate more data than was collected during the entire Galileo mission. Processing, storing, and analyzing this information requires computational resources that didn't exist when the mission was first proposed. By the time the data arrives on Earth, it will be processed by artificial intelligence systems that are still being developed today. This accelerating pace of technological change creates interesting tensions with the long timelines required for space missions. Spacecraft must be designed using technologies available at the time of construction, but they won't reach their destinations until those technologies are obsolete. The computers aboard Jupiter missions are typically less powerful than modern smartphones, yet they must operate reliably for years in environments that would instantly destroy consumer electronics. Future missions might resolve this tension through modular design and in-flight upgrades. Concepts for spacecraft that could receive new instruments or computational upgrades during their journey would allow missions to benefit from technological advances that occur after launch. The journey to Jupiter becomes less about sending frozen snapshots of current technology and more about creating platforms for ongoing evolution and improvement. The financial investment required for Jupiter exploration, spread across decades, reflects humanity's growing capacity for long-term economic planning. The total cost of all Jupiter missions to date represents roughly what the world spends on soft drinks in 6 months, yet the scientific and technological returns from these investments benefit society for generations. This return on investment demonstrates how space exploration serves as a forcing function for technological advancement and international cooperation. The careers of individual scientists working on Jupiter missions span multiple decades, creating unique forms of expertise and institutional memory. Linda Spilker, currently the project scientist for the Cassini mission to Saturn, began her career working on the Voyager missions in the 1970s. Her professional life encompasses nearly 50 years of outer planet exploration, representing continuity of human knowledge and experience that spans multiple spacecraft generations. This accumulation of expertise across decades creates scientific wisdom that can't be easily transferred or replicated. When veteran mission scientists retire, they take with them intuitive understanding of spacecraft behavior, knowledge of instrument quirks, and pattern recognition abilities developed through years of data analysis. Space agencies now invest significant effort in knowledge transfer programs designed to preserve this institutional memory for future missions. The gender and demographic evolution of Jupiter exploration teams reflects broader changes in science and society. Early missions were dominated by male engineers and scientists, but current and future missions include increasingly diverse teams that bring different perspectives and approaches to complex problems. The upcoming Europa Clipper mission has a deputy project scientist and several instrument principal investigators who are women, representing progress toward more inclusive participation in space exploration. This diversification of exploration teams connects to research showing that diverse groups solve complex problems more effectively than homogeneous ones. The challenges of reaching and studying Jupiter benefit from multiple perspectives, cultural backgrounds, and approaches to problem solving. The journey to Jupiter becomes not just a technological achievement, but a demonstration of humanity's growing capacity for inclusive collaboration on shared goals. The environmental impact of Jupiter exploration raises important questions about sustainability and responsibility that connect to broader concerns about human activity throughout the solar system. Spacecraft carry Earth materials to Jupiter, potentially contaminating pristine environments with terrestrial microorganisms. Planetary protection protocols require sterilization procedures that eliminate Earth life before launch, but these measures must be balanced against mission complexity and cost. Future missions to search for life in Europa's ocean face particularly stringent planetary protection requirements. The spacecraft must be sterile enough to avoid false positive detections, while robust enough to survive years in Jupiter's radiation environment. This tension between scientific requirements and technological constraints drives innovation in sterilization techniques, material science, and mission design that benefits applications far beyond space exploration. The ethical dimensions of Jupiter exploration extend beyond contamination concerns to questions about how humanity should behave as we expand beyond Earth. But have you ever wondered how long it takes to travel to Pluto, the distant dwarf planet at the edge of our solar system? In this in-depth video, we explore Pluto's distance from Earth, how NASA's New Horizons spacecraft made the nearly 10-year journey, and how future space propulsion technologies could drastically reduce travel time. It's a must-watch.